we are starting Unit 4, which is our unit on gas laws. And to start, I want to look at this picture. Does anyone know what this is called? That little instrument? No? Yeah, y'all do. A barometer, exactly. This is a picture of an old-time barometer where we're using mercury, and 1 atmosphere of pressure, normal atmosphere, if we're at sea level, is going to have the barometer measuring at a height of 760 millimeters of that mercury. That's where we get that unit of pressure that we're always used to. Does anyone want to take a guess? We're making these barometers out of mercury. Does anyone want to take a guess why we don't use water in this type of barometer? Water evaporates? No, yeah, but we could close it in a way where it wouldn't evaporate. Any other ideas? No. Nothing to do with temperature. Mercury's denser, so that has something to do with it. It has a lot to do with it. That's kind of the whole point. This tube here is not that much taller than 760 millimeters. If we were to do this with water, it would be huge, humongous, way big. So at the end of this lecture, I'm going to show you a picture. I was walking on Arkansas State University's campus. I was teaching there that week, walking through the science buildings, and one friend was like, "Oh, what's that?" And it was a tube in a bucket going up 3 stories high. And I got so excited. I'm like, "Oh my God, that's a water barometer!" And everyone thought I was nuts. I thought it was cool. But anyway, so I have one to show you. It wouldn't be quite as convenient as the mercury one. Miss Sage and I made a futile attempt to do it out my window, but we couldn't get the air bubbles out of the tube. It was a mess. But anyway, I'll show you a picture of the water barometer shortly. She was the first one I texted, by the way. I was so excited that I saw a water barometer. But anyway, so when it comes to pressure and it comes to units, you guys need to know the units of standard pressure and all the different conversions. You need to know atmosphere, which is going to be our most commonly used one because of the universal gas constant that has that unit in it. Well, the particular version of the gas constant we use is in atmospheres. Millimeters of mercury, 760 is equal to 1 atm. You need to know pascals and kilopascals, mainly for physics, more so than chemistry. The other unit that you're going to see today is torr. Does anyone know what that's the same as, pretty much? Millimeters of mercury. So torr is actually the same. So 760 millimeters of mercury is equal to 760 torr. Okay, so let's move on. We're going to go straight to talking about some relationships between our variables that change when we change pressure, temperature, and volume. There were some laws that we talked about last year. The first one being Charles's law. I know that those of you who had Miss Richardson did this. Charles's law is a relationship between 2 variables. Does anyone remember what they were? T and V, Charlie Brown, Charlie's Angels, Charles in Charge, they're all on TV. So Charles's law is the relationship between temperature and volume. You're not going to be tested on the AP as to what the name is. I just find it to be an appropriate thing to kind of know, and it actually comes up. I was in a CPR, I should tell the story after I go through all of them, but I was in a CPR training, and the instructor was, we were doing the compressions, and he's like, yeah, and Charles's law says that as the pressure, blah, 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 the volume. And I was like, no, shaking my head, raising my hand. And he goes, yes. I'm like, no, that would be Boyle's law. He's like, I don't think. I'm like, yeah, I think so. So anyway, see, it comes in handy. It made me feel really, really smart. But anyway, I digress. What is the relationship? As you increase the temperature, the molecules, that's supposed to be in here, the molecules move faster and faster and faster, spread apart. What happens to volume? Increase. So they are directly related. Okay? So let's talk about that Boyle's law. Let's see, who can I pick on? I think I should try Thomas. Thomas is getting ready for prom, and he's in the mirror. Do you shave? Not, yeah, okay, shaving. Just checking. He always looks so clean. He never has like the shadows. I never know. Anyway, shaving, putting on the cologne, slapping it on his face, and all of a sudden he sees a boil in the middle of his head. How does he feel? He feels peeved that he has a boil on his head. PV. So let's talk about that relationship. As we increase the pressure, what happens to volume? Think about a Nerf ball. Volume decreases. Good. And again, these are gas laws. Volume and pressure are not going to be big of a deal when we're in solid form because pressure is not going to affect solids that way. The last one is Gay-Lussac's. As Texans say, Gay-Lussac's law. Yeah. Gay-Lussac's. So, does she? Well, we teach together a lot, Miss Richardson and I. We kind of have the same sense of humor, too. So, we've got, I'm going to pick on my two Anns here. Annie and Ann, or Ann and Annie, however they want to be called. They're at the mall. And one Ann says to the other Ann, "Oh my gosh, look at the guy down there. He is so cute." And the other Ann says, "Oh, didn't you know he's gay?" So the first Ann's like, "Oh, what a pity." PT. PT, pressure temperature. All right. So as we increase our pressure, what happens to temperature? Molecules are closer together, hitting more often, hitting each other often, temperature increases. Or you can look at it as you increase the temperature, the kinetic energy increases, they slam into each other more often, and the sides of the walls more often, causing an increase in pressure. All right, so let's do some math. This is a version of a type of problem where you could actually use something called the combined gas law. And the combined gas law is something those of you who took regular chem used. Those of you in pre-AP did the dimensional analysis. However, I'm not going to stop you. If you want to use the combined gas law for any of these problems, you can. It's peas and vegetables go on the table. Peas and vegetables go on the table. Okay? Where these are initial conditions, and these are final conditions, and that's what we're doing in all these dimensional analysis problems. A condition of some sort or multiple conditions are changing, but we want to see how it's going to affect something else. My only issue is that you need to know that standard pressure is what again? 1 atm, and standard temperature is 273. Last class they said 298, which was correct if we were dealing in like thermochemistry or we're dealing in electrochemistry. Normally 298 is, but because we're dealing in gases, we want high temperature, low pressure. We want super, super cold. We want the molecules, if it's colder, aren't the molecules closer together? Aren't the samples more dense? So we're going to get bigger weights and larger samples to work with if we're at colder temperatures, okay? Another thing is we have to be in Kelvin when we do these problems. We'll talk about that more in a second. But let's take a look at this first example. A sample of SF6 occupies a container at variable volume. If the sample originally occupies the volume of 50 mils, so we know that this container has variable volume. It could be a balloon, okay? Variable volume means it'll change. So it starts out at a volume of 50 mils and 755 millimeters of mercury. Calculate the pressure, so we're looking for after. Calculate the pressure, which must be exerted to lower the volume to 25.0 mils. So we want to see the change from here to here. So this is my beginning conditions, and then these are my ending conditions. If you want to use the combined gas law, all you have to do is take out what variable is constant. And in this particular case, what's constant? When they don't mention it. Temperature. So you can cross temperature out and then just plug in your PV and solve. However, my problem with that is you're not really thinking about, does my answer make sense? So using dimensional analysis to me is the smarter way to go. To set up a dimensional analysis problem, you start with what we're looking for. What are we looking for? The pressure, right? So we're going to start with the pressure of 755 millimeters of mercury. Okay, so talk out what happens. Volume's going down. If volume's going down, What's happening to pressure? Pressure is going up. So I need to multiply this by a ratio of these two numbers that'll make it get, not these two numbers, sorry, these two numbers that'll make it get larger. Would that be 50 over 25 or 25 over 50? 50 over 25. Okay. So to 3 sig figs, what is my answer? 1,510, and the unit is millimeters of mercury. Let me talk through it one more time. We started out with this pressure. We want to know what happens to the pressure when the volume decreases. The volume decreases, so if volume decreases, pressure has to increase. So we're going to multiply this ratio in a manner that's going to give us a larger answer. This way we know it makes sense. If you just plug your stuff up into, in this case, we're dealing with Boyle's law, you know, you're not going to know. You have to stop and really think about, does my answer make sense? Here you're forced to do it without the whole, maybe I plugged stuff in the wrong way, maybe I didn't. Okay? But again, if you choose to do it that way, that's fine. Just show your equation before you substitute things into it, please. So now we're going to do some temperature problems. It's crucial that all of your temperatures, when you're doing your dimensional analysis or your combined gas law, they're all in Kelvin. They have to be in Kelvin. Why? Well, we didn't have to be in milliliters or liters before, or the pressure. I didn't say we had to change pressure to atmosphere or anything. So, Seth? So in order to keep all the temperatures positive, we need to do the calculations in Kelvin. Otherwise, we could end up with negative volumes and pressures, which are no good. So let's take a look at number 2. Let me move this down a bit. It says a 545 mil sample of nitrogen gas is initially at negative 220 degrees Celsius, and it's heated to 100 degrees Celsius. Calculate the new volume. All right, what do we want to do first? Change the Kelvin. See, I'll do that. I know that this is 373 off the top because math is hard. What about this one? 53 Kelvin. Okay, so we're going to start with what we're looking for. We're looking for volume, so we're going to start with volume. Okay, so we're going to see what happens from there to there. What's happening to temperature? Temperature is increasing. As we increase temperature, what happens to volume? Volume increases. So I'm going to multiply by a ratio to make volume increase. And that's 373 over 53. Kelvin cancel, leaving me with my unit of mils to 3 sig figs. Go ahead and give me, I know I'm ignoring sig figs. I'm pretending there's 3 in all of these because I don't want to think. So if you want to make all these 3, go for it. All right, what's my answer? Louder, please. 3840 mils. Okay, let's try this next one. I'm actually going to start it up higher because it tends to get a little bit messier because we're looking at now multiple conditions changing. It says calculate the volume of a sample of helium at negative 33.0 degrees Celsius and 1.23 atm if it occupies a volume of, so we're looking for the volume here. I'm going to put a question mark volume because it says calculate the volume of a sample with these conditions. If it originally occupied a volume of 2.34 liters and 54.5 degrees Celsius and is 1026, there's a couple of issues here. What's the one I always want you to take care of first? Kelvin. So what's negative 33.0? 250 Kelvin. And what's 54.5? 3 327.5 Kelvin. Okay. It's not 250 here. 248. Oh, I lost all that stuff. Negative. This was originally negative 33. So what is this? 2 what? $240 Kelvin. Okay. So I see another problem. Who sees it? These have to match up. Just get used to converting to atmospheres. Not that I'm going to make you. If you wanted to convert the atmospheres to millimeters, you could. But atmospheres is the common pressure unit and the universal gas constant we use the most. So I just want you to get used to dividing your millimeters of mercury or torr by 760 to get atmospheres. So what's the number of atmospheres? 1 point what? 1.35 ATM. All right, now we can start our problem, but this one's just a smidge different by the way we set it up. This is the original volume we have. When we change things to this, the question is, what's the new volume? So we're actually going the other direction. We're going to here. So start with what we're looking for. We are looking for volume, so I'm going to start with volume, and I'm going to start with 2.34 liters. Now, don't try to overthink this and do everything at one time. We're going to take one condition at a time. And do you want to start with temperature or pressure? I don't care. Temperature. So from here to here, temperature is decreasing. What happens to that volume? Those molecules get all cold and they huddle up. Volume decreases. So what's my ratio? 240. Is it 240 or 246? Oh, it has to be 240. Duh. 240 Kelvin over 327.5 Kelvin. So we're done with temperature. Wipe it out of your brain. Now go to the next. What's happening to pressure? Pressure is also, no, we're going from 135 to 1.23 atmospheres. 1.35 to 1.23 is decreasing. What happens to volume as we decrease pressure? Volume increases. So we want to multiply by 1 point. So these are kind of fighting each other, right? Or are they both going the same direction? They're both going the same direction. No, they're not. They're not. They're fighting each other. So who's going to win? Well, it depends which one creates the larger multiplier. So give me 3 sig figs. 1 point and the unit on that, everybody? Liters. Good. Next, I want to look at the thing we call Dalton's Law. Dalton's Law of partial pressures. This is not hard. It's really kind of a common sense sort of thing. Dalton's Law basically states that the total pressure of a system is equal to the partial pressures of all the gases in that system. So if I ask for the total pressure of the gas in this room, it would be the pressure of the oxygen and the nitrogen and the CO2 you're breathing out and all that stuff all added up together. And the methane. Some of you had lunch. Beans, maybe. I'm just kidding. Tanya's all grossed out. She's like, hey, it's life. It is what it is, you know? We all are people. We all do those gross things. But we don't talk about it like I'm talking about it. Yeah, we just don't discuss it. Okay, because I'm not a middle school boy. So, as far as applications, sometimes you'll have really simple Dalton's problems where they'll say, what's the total pressure of the system if the partial pressure of one gas is this, that, and the other? You just add them up. Okay, we're not going to practice that, but we're going to practice the more common use of it. And that's when you see a problem that says collected over water. When you see that, you need to go, ugh, and stop yourself and go, yeah, now I have some work to do. All right. Most of you took pre-AP, so I know you guys collected gas over water. Okay. I know you collected hydrogen, and I know you made it bark, right? Okay. So what you did when you did that, you had a sink or a bin, and you had your hand sticking in the water. I'm gonna make it look like an elephantitis hand, and in your hand you had an inverted test tube, okay, and out of that tube was a hose that you were holding with your other hand. Do I have to draw the other hand? Holding the hose, okay, and that hose was attached to a reaction vessel that had some sort of gas being produced. And you did, I think you just did hydrogen, right? I don't think you did oxygen. Or did you do oxygen? Did you do different ones? I know, yeah. So, you collected the gas, and the gas displaced the water. So water, this was originally filled with water, and water was coming out while gas was going in. So when you were done, let's say you were collecting hydrogen. Yeah, you had hydrogen gas in there. But one thing you really didn't talk about, and y'all did these calcs, but you didn't really talk about what was going on here. You also had water vapor in there as well. So whenever we do problems like this, the total pressure of this whole thing is both the water and the gas. Well, we usually just want the pressure of the gas alone, so we have to subtract off the water vapor pressure. And that's something you guys are going to do, and you're going to be either given the water vapor pressure, or you're given a table, and you have a copy of a table at the very last page of your notes. So that's something we're going to reference in just a second. So let's do this problem then. Experimentally, oxygen gas is frequently collected over water. Collected over water. When a sample of oxygen produced from a chemical reaction is collected over water at 24 degrees Celsius, the total pressure, this is pressure, this is temperature, be careful here, this is pressure total, was 765 millimeters of mercury. Calculate the pressure due only to oxygen. So is temperature changing? Okay, so this is actually really simple. Okay, no temperature change. We want just the pressure of the oxygen. Well, this is pressure total. What is pressure total equal to? Pressure of oxygen plus the vapor pressure of water. So we're going to take our total pressure, which was 765, and I'm just plugging it into this formula here, is equal to, we're solving for the pressure of O2, and from your nifty tables, what did you get as the pressure of water? You've got vapor pressure at that temperature. Now, we got an issue. This was in millimeters of mercury. And again, when you're looking at your vapor pressure table, you look up at the temperature of 24, and that's how we found the 22.4. But anyway, there's a problem. What is this problem? Is it really a problem? It's actually a nice problem to have, because yeah, we're in different units, but isn't torr and millimeters of mercury the same in terms of value? Okay, so, yes. So when you do this subtraction, what's our final pressure? Just give me 3 sig figs as the partial pressure of oxygen. $742.6. When you're writing partial pressures, they're actually pickier than I thought. I didn't realize this until I started grading the AP. They're really picky about it being a P with the O2 as a subscript. That means partial pressure. That means there's other stuff in the system as well. So get used to writing that. Every time she changes pages, it freaks out on her. All right, so now we're going to do a full-blown one of these where we have to take a lot of stuff into account. This first problem says a 235 ml sample of gas, so that's our volume, was collected over water at a temperature of 28 degrees Celsius on a low pressure day of 738 torr. It's like a meteorologist. All right. Report what volume we'd have at dry STP conditions. What's your STP condition for temperature? Okay, and then torr, 760. And one thing I want to do immediately is get this thing fixed. This 28. How many Kelvin is this? 301. Okay, so that's taken care of. Now, with this whole water thing, if you look at the problem, it says what was the pressure of the day that we did the collection, the overall pressure? 738. Okay. Now I know that this is confusing to people, but think about this. If you're collecting a sample in the back of the lab and you get the gas in the tube and you pull it out of the water, do we understand that the total pressure in the tube is equal to the atmospheric pressure? Otherwise it would like either be sucked in or pushed out, right? So the total pressure in the tube is equal to the atmospheric pressure. So don't let the fact that they're saying it's the pressure of the day, that means that's the atmospheric pressure, which is equal to the pressure of your tube. And again, what was in that tube? The pressure of the gas collected plus the pressure of the water vapor. Okay, so that's the P total right here. Okay, so in order to get the correct pressure, what do we need to do? We need to take that 738 and subtract off the pressure of the water at 28 degrees. Looking on the table, we get 28.3 torr as the vapor pressure of water at 28 degrees Celsius. So when we do the subtraction, 738 minus 28.3, what is our pressure of the gas? .709.7 torr. So yay, now we can actually start our problem. And it's just like every problem we've done. We start with what we're looking for. We're looking for volume, so we are going to start with volume. So 235 mils. Okay, what do you want to start with, temperature or pressure? Temperature. As we go from start to finish, temperature is decreasing, so what's happening to volume? Volume's decreasing, so I want a ratio of 273K over 301K. Temperature's done. Now let's look at pressure. Pressure, we're going from 709 to 760. Pressure is increasing, so as pressure increases, volume decreases, so I want to multiply by 709.7 torr divided by 760 torr. And to 3 sig figs, my final volume is, louder, 191 units, 99 units, mils. Yay. So really quickly, I'm going to reintroduce to you the ideal gas law. You're going to use this a lot in physics when you get to gases there. I say pervnert. Some people say pivnert. I think pervnert sounds more like pervert, which is funnier than pivnert because it doesn't sound like, what, pivot? Pervert's funny. So pervnert is, it's important to know what units to use, and it's based on this R. This R is called the universal gas constant. And the units on that are liter, atmosphere, over mole K. And I actually got this from Sam Houston. You can tell her this is her glory in my mind. I say latamolk. That's how I remember latamolk, the units. Okay. It's important to know what the units are because that's going to dictate what units you put in for the volume, the pressure, the molarity, the moles, and the temperature. Okay. This is used, unlike the combined gas law, to just find one condition. Conditions aren't changing. Okay. In the last problems, you wanted to find conditions when other things were changing. Here, we got a set situation. We either want to solve for one of those variables. Okay. All the equations, the ideal gas law and whatnot, came from combining two of those together with moles being constant and R being constant. So that's where the relationship of Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law came from. And I could sit here and derive them all, but no, not so much. Don't really want to. So let's go ahead and practice this using PV equals nRT. Now, those of you who took Rozier probably did this with dimensional analysis, where you took the R and you put it in the railroad track. You can do that if you want. I prefer to use an equation for this just because I'm used to it. So what is the pressure required? So we're looking for pressure. Okay. I'm just going to plug stuff into the substituted equation, just like in physics, the kung fu thing that y'all do. Of an ideal gas, it's 0.460 moles, so I'm going to put that in for N. Assuming you all remember that that's, what was the gas constant? 0.0821 lat/mol. Okay. And then temperature is, now here's the deal, this is in degrees Celsius. We have to be in Kelvin, right? On the AP exam, you have to show not only substituting into an equation, you also have to show unit conversion. It is totally acceptable for within your substitution to write this. As a grader, I love that because I know you converted, I know you know how to convert, and you substituted in all at the same time. If you're uncomfortable with this, go ahead and do it to the side and then put it in the equation. And then, do I have a volume? Oh, 9.50 liters. All right, so let's go ahead and solve for that pressure. So this comes out to be approximately 1.22 atmospheres. Any questions? Yay, we have one more problem to do. Let's move on. All right, this one, you probably know the answer without even doing it, but I'm proving it to you using ProvNerd. Determine what volume 1 mole of gas at STP would occupy. Do y'all know the answer to that? Ooh, I hear it. Let's prove it, though. So, at STP, what would our pressure be? 1 what, dog? 1 atm. Good. We're looking for the volume. 1 mole is what they're asking. The 0.0821 is the lat/mol, our universal gas constant. And then our temperature at STP is 273. Ooh, lo and behold, what do you get? 22.4 liters. Wow. And that's the case. You guys learned that 22.4 liters is the volume that any gas, no matter what it is, has if you have 1 mole at standard conditions. Okay. Up on the top of my shelves, do y'all see that beach ball? That's a 22.4 liter beach ball. We will at some point play with it. We're out of time today. But normally we see what class can keep it up the longest sitting in their seats without it hitting the ground. Because that's very educational. All right, so tomorrow I'm going to introduce you to a new character. And we're not going to do this problem. Just jot this down. This problem, anytime we're looking for density or for molecular mass, we're going to use the molecular weight kitty cat. I'm going to introduce, did I hear a meow? Was that you're excited about the misspelling, the liberty I'm taking? Yeah, molecular weight kitty cat. And there's the kitty cat up high in the litter box up there. And so I'm going to introduce, this is a great formula to use when you're trying to find density or molar mass of a gas. Okay, that's it for the day.